Hello and welcome. This video is meant to accompany the AP Physics 1 review packet for energy free response. This would involve work, changes in kinetic potential energy, and conservation of mechanical energy. Let's get started. Please remember to pause or rewind the video as necessary. In problem number 1, it says each part shows a set of energy bar graphs that are in sequence. Explain a situation where the energy of a system could be represented by that sequence of bar graphs. Draw a diagram to help your explanation. As you explain the energy transformations, reference the diagrams using 1, 2, etc. If the total energy of the system changes, explain what external force does work to change the energy of the system. Note that K sub T represents translational kinetic energy, U sub G represents gravitational potential energy, and U sub S represents the potential energy of a spring. Part A. If you look in Part A, Diagram 1, bar graph 1, starts with 4 units of gravitational potential energy. Since you start with no kinetic energy, and what I'm going to do is I'm going to explain it by writing notes underneath each bar graph. In number 1, the object starts from rest How do we know this? Because translational kinetic energy is 0. You can see there's no kinetic energy there. From some height h. Again, we know this because you are starting with 4 units of mgh, gravitational potential energy. Now, if you look at picture 2, you have completely reached the bottom of whatever the situation is. And the reason we know that is we are no longer have gravitational potential energy like we did over here. We have 0 gravitational potential energy. And notice, of course, nowhere in here do you have a spring, so we don't need to worry about that. But what we do know is the object has reached the bottom, presumably bottom of a hill. And let's just use that as an example. That'd probably be an easy example. Object has reached the bottom of the hill, as we can see gravitational potential energy equals 0. But since KT is not 4 units, something you ladies and gentlemen should notice. If KT were 4 units, like it should be, then all of the potential energy converts to all the mechanical energy. But clearly there's a loss in mechanical energy here as you went from 4 units to 2 units. So since the translational kinetic energy is not 4 units, there is a loss in mechanical energy which would be work done by friction. So even though this situation would have to be some sort of a hill or incline or slope of some sort, it would have to be a rough surface because we're losing mechanical energy as the object goes downhill. And then finally, in bar graph 3, you can see the mechanical energy is completely dropped to zero. Since the mechanical energy has completely decreased to zero, the work done by friction continues to act on the object at the bottom. And we know this because the object obviously comes to rest. You have some kinetic energy at the bottom when you reach the bottom of the hill, but you can see at this moment here, we have no kinetic energy, no potential energy, no mechanical energy whatsoever. The object comes to rest. Pretty simple diagram right there. Just draw a hill. Some height h above the ground, and I'm just gonna draw little lines like this to indicate rough incline. And I'll just draw a block on there, that's fine. Rough incline, and this part right here would be a rough surface. So both rough surfaces, but this scenario would describe the energy, the total mechanical energy of 4 units decreasing to zero. Part B. The object starts with no mechanical energy whatsoever. So we're obviously starting from rest, and we're starting at the bottom or the lowest point. So an easy way to start this scenario would be the object starts from rest on the ground. Now you can see we have gained a little speed, little kinetic energy, but we've also gained height in this process too. So object accelerates upward. We can say, and that could be a perfectly good example of this would be like a rocket lifting off. The rocket is gaining speed and gaining altitude in the process. Rocket speeds up. Going up. And then, of course, in scenario 3, what do you have? You have more kinetic energy, more potential energy. Essentially, rocket's getting higher. Rocket continues to accelerate upward as it increases in height. So I suppose if I go back to diagram 1, this would reference diagram 1 being at the top, starting from rest. If I draw the block here at the bottom, that would reference diagram 2, lost some kinetic energy there, and then drawing the block way over here at the end, coming to rest, would be diagram 3. So similarly, if we could draw 3 diagrams here, so diagram 1, and just draw a rocket on the ground, rocket rocket taking off, rocket higher. Let's see now, part C. Now, if you look carefully, we're starting with some spring energy there. But we're also starting with some height above the ground. We start with potential energy, gravitational potential energy. We start with height. We start with spring energy. That means we start with involving a spring. So here's most likely what we have. Object starts from rest. How do we know this? Translational kinetic energy equals 0. But it starts from rest at height h, as gravitational potential energy is 3 units. So height h above the floor. And has spring potential energy. Mass is at rest and is spring loaded on a table height h above the floor. Now, if you pay attention to what's happening here, the gravitational potential energy stays the same, which means the object is still on the table at this second time. But all the spring energy has transformed into kinetic energy. So most likely what has happened is the object has slid across a frictionless tabletop. Since all of the spring energy transforms into translational kinetic energy, we know the object slides, well, first of all, the object accelerates and slides across a frictionless tabletop. Now, how do we know it's a frictionless tabletop? Well, if there were friction, you would have lost mechanical energy here in the process. Now you can see you have a total of 2 plus 3 or 5 total energy units. Since mechanical energy is conserved, you can see now that all 5 energy units have completely transformed into translational kinetic energy. Right before the object hits the floor. We know this because we have a potential energy of 0, which means the object is right above the floor. So what would the diagram of this look like? So here's the floor of the whole situation. Let's draw a table. And maybe some wall over here with a compressed spring, and that would be the mass at part 1. And if we look at the mass at part 1, it's height h above the floor, giving it some gravitational potential energy, and you have a compressed spring right here, giving it some spring potential energy. Now, if we draw the block sometime later, here at position 2, that would account for the same height above the floor, but it would count for the spring energy completely transformed into kinetic energy. In other words, the object is moving at this point. Now, at this point right here, the block will fly off the edge of the table as a projectile, and right before hitting the floor, the block no longer has the potential for gravity to do work, meaning the block no longer really has gravitational potential energy, as we can see. And at this point, all 2 units of translational energy that it has right here, plus the 3 units of gravitational potential energy, all become the translational kinetic energy of the block right before hitting the floor. And that would be position 3. In part D, we start with 3 units of translational kinetic energy, and that completely converts to 3 units of gravitational potential energy. And it gives us a clue here that this process repeats over and over. Now, that must be some sort of oscillation, some low amplitude oscillation. When I say low amplitude, I'm saying the lowest possible amplitude would maintain the oscillation over and over again. So we're looking at simple harmonic motion, most likely with a pendulum. I'm going to actually draw the diagram for this one first. So I'm going to draw the diagram here, the pendulum at its lowest point. And then I'm going to draw the pendulum at one amplitude. And then the pendulum at the other amplitude. And so what happens is, if you look at this here, you're starting with kinetic energy, which means the amplitude is at its lowest point. It could be like a child on a swing, and somebody comes from behind the child and pushes the child forward to give the child a swing. Or it could be something as simple as a ball hanging from a rope, like a tether ball, and all of a sudden somebody strikes the tether ball and it starts swinging up at an angle. But clearly what's happened is you're giving this some kinetic energy, and it's going to swing to its highest point here, and then it's going to come back and swing all the way over to this side, and then it's going to repeat like this. Now, this would be situation one, where you're starting at the bottom. How do we know we're starting at the bottom? We're starting with no potential energy, and you're starting with kinetic energy. So you're starting at the equilibrium position, and position two, you're ending up at the amplitude position where you have maximum potential energy, and you stop since you have no kinetic energy. So position two would be up here, and technically it'd be up here too. Okay, so description-wise, we can write a pendulum is at rest at the equilibrium position. It is given a push right? How do we know this? Because of the initial kinetic energy. And swings upward. Well, at this point, at position two, the pendulum has swung upward. To its amplitude position. Again, let's practice using these physics buzzwords like equilibrium and amplitude. And momentarily stops. How do we know it momentarily stops? Because the translational kinetic energy is zero now. The translational kinetic energy in diagram one, has completely transformed into gravitational potential energy. In part E, you're starting with spring potential energy, and it's converting into translational kinetic energy. Since there is no change, since there really is no gravitational potential energy and there's really no change in it, essentially this must be some sort of oscillating mass spring system on a horizontal surface. So we're looking at a horizontal mass spring oscillator. Again, I'll draw the picture first. The equilibrium position is in the middle with x equals 0. One amplitude we'll put over at this side. The other amplitude is equidistant from the equilibrium on the other side. And you can either start at maximum compression or maximum stretch. It honestly doesn't matter, but you're starting at one of the amplitudes. I'm going to go ahead and start it at the maximum stretch. That's going to be position 1. And then I'm going to draw the block again, passing the equilibrium position, and that's where you have maximum kinetic energy and 0 potential energy. That would be position 2. And then back over here, having the block over on this side, would be back to position 1. Okay, and we can describe this as a mass is attached to a horizontal spring and is stretched and held at rest. Why do we know this? Again, because there's no translational kinetic energy to start with. The translational kinetic energy completely transforms into, I misspoke. The spring potential energy completely transforms into kinetic energy as the mass slides past the equilibrium position. In part F, we appear to be starting with gravitational potential energy, so the object is starting with some height. But again, if we look at the clue here, it's saying 1, then 2, then 3, then 2, then 1, then 2, then 3, then 1, then 2. It's going like this. 1, 2, 3, 2, 1. This is some sort of oscillatory system too, but it involves a spring. So since it involves a spring and it involves changing gravitational potential energy, we are talking about a vertical mass spring oscillator. So in part 1, mass is attached to a vertical spring and held at rest at its highest point. Now, if you look, the potential energy cuts by half, which means the height cuts by half. So now the mass has fallen half the way down. Right? We know this because the gravitational potential energy is half. Gravitational potential energy increases, and spring stretches, right? We know this because your increase in spring potential energy. Then finally, we have the object comes to rest. It's clearly at its lowest point, and you clearly have full stretch and full spring potential energy. The mass comes to rest when the spring is completely stretched at the lower point of oscillation. So if we were to draw a picture of this, in diagram 1, you'd have a mass that's just being held. Diagram 2, the mass is halfway down. It's moving, there's kinetic energy, and you have some stretch in the spring too. And then lastly, your spring has gotten to its lowest point. Comes to rest, but you've got full stretch, so you have full spring energy. In part G, we're starting with spring energy. You're starting from rest, no kinetic energy, and you're starting at the lowest point. You're starting on the ground. So let's translate that bar graph into words. An object starts from rest, because we know KT equals 0, on the ground. We know this because UG equals 0. The object is spring-loaded. We know this because we have 3 units of spring potential energy. Now, if we look, that spring energy is completely transformed into kinetic energy. There's no loss in mechanical energy, so what we know is the object accelerates on a frictionless tabletop or a frictionless, say, a frictionless surface, because there is no loss in mechanical energy. Spring potential energy completely transformed into translational kinetic energy. And then lastly, the translational kinetic energy completely transforms into gravitational potential energy, which means the object most likely goes uphill. There's no more spring involved, and the object comes to rest. So the object moves up a frictionless incline Again, how do we know this? No loss in mechanical energy. And comes to a stop at its highest point. Again, we know this because translational kinetic energy is 0. Diagram could look something like this. Got a wall, surface, incline, some height h above the ground. Mass starts here, spring-loaded at rest. Mass completely gets to the end here with some movement. Mass reaches its highest point and stops. In problem 2, it says a student wishes to determine the spring constant K of the spring inside of a marble launcher. The student builds an experimental setup shown in the diagram, where the marble launcher will project the ball horizontally after the spring has compressed a distance x. The student measures the spring compression x for 5 trials. And for each trial, the student also measures the horizontal distance d that the ball travels once it becomes a projectile. The student also measures the height from which the ball is launched to be h equals 0.8 meters, and the mass of the ball is to be 0.03 kilograms. Use 9.8 meters per second for g. This problem has 2 concepts associated with it. Concept number 1, and if you look over here at the edge of the problem, since you have kinematic variables dealing with this flying over the edge, this is a horizontally launched projectile. Okay, but it's also a conservation of energy problem as well, Because as we can see, we have spring-loaded energy. We're going to have spring potential energy. It's going to convert into translational kinetic energy at the bottom here. And you're also going to, of course, going to have gravitational potential energy. So you have spring and gravitational potential energy will convert into essentially translational kinetic energy as it flies over the edge. So we have transformations in energy associated with this problem as well. So we're going to be going back and forth between conservation of energy issues and ways to solve problems that way, and horizontal launch projectile. So let's actually begin this problem by taking a look at the energy side of things. When it's a conservation of energy problem, it's always good to break it down into two areas that the problem will have essentially an initial part and a final part. And the mechanical energy, the total mechanical energy, remains the same if there's no friction involved. Now, total energy remains the same regardless, but mechanical energy will remain the same when there's no friction, no loss of energy due to friction. So over here, we can actually designate this as the initial point and call this energy initial. And that's going to be broken down into, you've got, and I'm going to designate the gravitational potential energy to be 0 here, because you can make that 0 any place you want it to be. And the reason I'm going to do that is because I'm going to make this the final point, and I'm going to suggest that the final potential energy is also 0. Notice when it reaches the end of the tube, there's no change in height. In other words, I'm only going to have the conservation of energy problem confined to just this tube right here and the changes of energy within the tube. Because the rest of this problem will be a horizontally launched projectile. Well, what else do I know? I also know that there's spring potential energy initially. 1/2 kx squared is the equation for that. And that there's no initial kinetic energy because we're essentially releasing it from rest. But what I also know is that when the ball reaches this point here, all of this has completely transformed into kinetic energy, 1/2 mv squared. And since the spring is no longer being compressed, the spring energy converts to 0. So we're going to be using these to set up part of the problem at a later point. But it's good to initialize your problem with the energies at an initial and a final point before you even engage with the problem. It just kind of gets you thinking about where the problem will head once you get there. Well, in part A, it says write two equations that relate d and h to the initial speed of the ball as it becomes a projectile. So now we're talking about horizontally launched projectile, horizontal projectile motion. And with horizontal projectile motion, there are essentially two equations that end up being used. Equation number 1 is y equals y naught plus v naught yt minus 1/2 g t squared. That is at least how we remember to write it. V naught y off the edge is 0 because you're only going with v naught x. Okay, you're only going with horizontal velocity off the edge, so there is no vertical velocity, so we zero that out. And I'm going to let the y at the bottom be 0. I'm going to let y at the bottom be 0. I'm going to let y naught equal h. So y naught's going to equal h. And so I end up with 0 equals h minus 1/2 gt squared, which means h equals 1/2 gt squared. That's kind of an easier equation to remember for horizontal launch projectiles, but you can always start here. That's fine too. And if we solve it for, we're going to want solve it for time in a minute, but for now, we'll go ahead and leave it in this form here because all we're asked to do is just write the two equations. The other equation that we need is the horizontal direction, x equals v naught x times t. But writing it in their variables, x is really this distance over the edge right here, d. So x becomes d, and v naught x just becomes v over the edge times t. That's your basic constant velocity equation of distance equals velocity times time. Now in part B, this is exactly where we needed to use the conservation of energy idea because we have to write a conservation of energy equation. So let's go to the work that we just did up here. The conservation of energy equation tells us that the total initial energy equals the total final energy. Well, the total initial energy is our spring potential energy, and that would be 1/2 kx squared. And that is going to equal our final kinetic energy of 1/2 mv squared. Now we're just going to use some substitution here, and we're going to combine all three equations that essentially relate those five variables. Distance over the edge of a projectile, x, the compression of the spring, g, the acceleration due to gravity, height, the h above the floor, and k, the spring constant. So here's where we can start. I'm going to take our conservation of energy equation, 1/2 mv squared equals 1/2 kx squared, and I'm going to lose the halves. And I'm then going to solve for v. So to solve for v, I'm going to divide by m and square root. So v is equal to the square root of kx squared over m. And I'm going to hold off on that for a second. And then I'm going to take this other equation that we wrote over here. H is equal to 1/2 gt squared. And I'm going to solve that for time. Well, I'd have to multiply by 2, divide by g, and square root. So t is equal to the square root of 2h over g. Now, if we take this and put this together, d is equal to v times t. Well, here's your v. The square root of kx squared over m, and there's your t. Square root of 2h over g. Put that together, a radical times a radical, you just put all that stuff under the radical, and the distance of the projectile d is the square root of, I'm going to pull that 2 out in front, I guess, and 2khx squared over the mass, over the mass times g. Now, what quantities should be graphed in order to yield a straight line relationship with the data? Well, remember the variables. The variables that the student was measuring were x. Go back to the data here. They were measuring x. Student measures compression x, and the student also measures distance d. Okay, so those are the only two variables. Everything else should be a constant. So what we're going to do is we're going to take that whole equation, and we've got d is equal to the square root of 2khx squared over mg. First thing I'm going to do in order to reason this out is I'm going to get rid of that square root. And we're going to do that by squaring both sides. Okay, rewrite this, everybody. We're going to go have d squared equals And then, of course, the 2 just cancels the square roots of everything under the radical. So 2 kh(x squared) over mg. And again, what did the student measure? And I'm gonna write in blue above the measurements. The measurements were distance d, that's a variable, and x, the compression, that's a variable. Above the constants, I'm going to write the letter C in gray. So I wrote variable of the measurements, and I'm going to write C above the constants. Well, 2 is obviously a constant. The spring constant K is obviously a constant. The height that it was launched from above the floor was a constant. The mass was a constant, and G is a constant. And so if I essentially divide both sides by the x squared, like this, I get the following. I get my relationship. I get rise over run, which is, of course, my slope. My rise would be what? D squared over x squared, right? So I divide x squared to the left side. And that's left equal to, that is equal to 2 times k times h over mg. That, ladies and gentlemen, is what my slope will equal to. So the question's asking what quantities need to be graphed: d squared versus x squared. Okay, so what I need to do with this data is I need to essentially square all my x's and square my d's. So this data right here is no good. This is a typo. So I'm just going to cross all this out right here, and I'm going to write new data values beneath each of these crossed out numbers. So in this one, if this is spring compression x, this would be x squared in square meters. And if this is distance d, this would be d squared also in square meters. So let's go ahead and do that. If I square 0.1, so if I square 0.1, I get 0.01. If I square 0.15, I get 0.0225. If I square 0.2, I get 0.04. Squaring 0.25, I get 0.0625. And if I square 0.3, I get 0.09. Okay. Now, if I square my horizontal distances, squaring 1.24, I get about, it's actually about 1.54. If I square 1.9, I get about 3.61. If I square 2.61, I get about 6.81. Yeah, about right there. If I square 3.14, I get about 9.86. And if I square 3.84, I get about 14.7, roughly. Okay, so now, again, I'm plotting d squared on the x-axis in square meters, x squared on the y-axis, also in square meters. And look at your data. I'm going up to a maximum of 0.09. Since there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines, kind of makes sense that I would make each one probably about 0.01. So this would be 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09, and 0.1. Right? That would be the range, the scale, and the intervals of my x-axis. My y-axis is my d, and I look here to my lowest data point in the data table is my highest data point for d squared, and that is 14.7. So I'm going to go from 0 to a number slightly higher than 14.7. Well, I mean, I could essentially make each box, I could go by twos. I could go by twos all the way up. So this would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. That's not too bad because my highest data point is about right here. You want to try and stretch out your data as much as possible. Now you're going to plot. So your first plot point, we're going to go over 0.01 and up about 1.5. First data point's about right there, roughly. Again, you're estimating. Next, you're going to go over about about 0.02 and a quarter, and up a little over 3.5. So here's 0.02 and a half. This would be 0.02 and a quarter. So 0.02 and a quarter, and then 3.5, be roughly about there. And then we're going to go over 0.04 and up almost 7, 6.8. So we're over 0.04. We're up to almost 7. So it'd be roughly about there. Then we're going over 0.06 and a quarter and up almost 10. So we look at it here. This would be 0.06 and a half. This would be 0.06 and a quarter. And we're going all the way up to almost 10. Whoops. Try that again. And roughly about that point right there. And then last data point, we're going over 0.09 and up almost 15. So up 0.09 and up almost 0.15. So roughly about there. Okay, and you've linearized your data. What we're now going to do is we're going to draw a best fit line through that data point, through those data points, and we're going to find the slope of that best fit line as best we can. Okay. Now your slope doesn't have to go through 0, 0. Don't try and force it to go through 0, 0. Mine just happens to go through 0, 0 at this point. So what I'm going to do is I'm going to take my slope from the bottom here to where it's intersecting that point right there. So I've got a rise of about 10 and a run of about 0.06. Okay, and so that's going to be my slope. So the first thing I'm going to do is I'm going to find that slope. My slope and I'm not going to use M for my slope. I'm actually going to write the word slope, because if I write the letter M, that could be confused with mass. So best to just write the word slope. So my slope is going to be my rise over run. In this case, it's about 10 over 0.06 roughly. And 10 over 0.06 is roughly approximates to about 167 newtons. Now we'll get into what the actual value of this is in a minute. But now from this, what are we going to do to actually get K? How do we determine K, the spring constant, right? That's what we're looking for from the slope. So if you remember above, what we came up with, the slope is actually equal, the rise over run is equal to 2kh over mg. So let's write that little fact down. The slope is equal to 2kh over mg. So how do we isolate for the slope? Well, we have to multiply by mg and we have to divide by 2h. So essentially k would be equal to mg times whatever your slope is, which in this case is 167, over 2h, right? And then we're just going to plug in that. So K is going to be equal to the mass, which was 0.03 kilograms. That was given in the problem, times G, which we were asked to use 9.8, times the slope, about 167, over 2 times 0.8 meters. Okay, and let's see what the approximate spring constant would be. So we're going to go 0.03 times 9.8 times 1.67, and we're going to divide that value by 1.6, which is 2 times 0.8. And I'm getting roughly about 30.68. We could say 30.7 newtons per meter, or maybe just round it up to 31. That'd be fine too. The nice part about doing work like this is called a data processing lab-based question. And in data processing lab-based questions, you're almost always asked to find some physical meaning and physical value involving the slope of a best fit line of the data. And so you're given an acceptable range in which your answer is allowed to fall in. And your range should be essentially the value that it's expected to be plus or minus 5%, essentially. So they do give a little bit of wiggle room for differences and possible error. Now, to get a different measurement of the spring constant, the student removes the spring from the marble launcher and hangs it vertically. The student hangs different amounts of mass on the spring and measures the length of the spring when the objects are in equilibrium. Well, ladies and gentlemen, this is a Newton's first law problem. This is a Hooke's law lab. And essentially what you'll end up doing with this, if you take a look at my picture right here, you're simply going to hang mass on a spring. You've got the weight going straight down, and you've got the spring force equals kx going up. And you're simply equating those two, kx equals mg. So what we're going to be doing, and according to the variables they're using the spring length is L, not X, but KL equals mg. And so how can we get K? Well, K, if we solve for it, is mg over L. So if we are changing the mass and we put the mass right here, and we can do the mass times g and get the weight. There's a bunch of ways we could do this. Okay, this is just one possible way. But one possible way is to multiply each mass times g and essentially get the weight, and that would be our rise, our y-axis, and the length, the x, how far it's stretched, is the run, the x-axis, and the rise over run is your slope, and that's your k. That's your spring constant. Okay, so the slope is the spring constant. We don't have to do anything with it. That's probably the easiest way to get this result. Okay, another possible thing we could have done is we go k times L equals mg, and you again figure out, well, my length is a variable, mass is a variable, g is a constant, k is a constant. And so I can get k over g equals m over L. And so if I just simply plot m versus length, my slope right? Because remember, this is equal to slope 2. My slope is equal to k divided by g. So in other words, what would I need to do? To get k, I would need to multiply my slope times g, or do that. So there are several ways in which you could accomplish finding the spring constant doing this way. I'm going to go ahead and use the first method because I like the idea of my slope just equaling k and then being done with it. So in order to do that, I need to find mg. So we've got our hanging mass. I'm going to find essentially the hanging weight in newtons. Okay, and so that would be the weight, or I guess we could say mg. And then you still have spring length x, or spring length L, I guess what they're calling it in this problem. And that's in meters. So that I'm just going to copy down exactly the way it was because I don't need to change that. The hanging weight, on the other hand, I need to multiply each of those masses times 9.8. So 0.2 times 9.8 would be 1.96. 0.4 times 9.8 would be 3.92. 0.6 times 9.8 would be 5.88. 0.8 times 9.8 would be 7.84. And 1 times 9.8 would be 9.8. Okay, so this is my y-axis. This is my x-axis. So I've got weight in newtons. And on this axis, I've got length in meters. Start with the x-axis. Your highest data point is 0.428. So we can go from 0 to about 0.5. But this time I'm going to probably skip some boxes in order to do it. Because if I go 0.1, 0.2, 0.3, 0.4, 0.5, that only uses half the graph paper. Why do that? Spread it out. 0.1, 0.2, 0.3, 0.4, 0.5. See, I'm using every 2 boxes in order to accomplish this. And then similarly, I'm going to pretty much about 10, so I can just easily make each box 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Plot your data. Okay, so we're going over a little over 1.5 and up almost 2. So a little over 1.5 up almost 2 puts us about right there. Whoops. About right there. Then we're going to go over about almost 2.25 up 4. So this would be 2.25. 2.23. So 0.25 is 2.25. So 0.23 is less than that. So a little bit less, and then up almost 4. 3.92. So about right. Try that again. Then we're going to go over 0.3 and up almost 6. Then we're going to go over about 3.5, 0.3.5, and up almost 8. Then we're going to go over basically about 0.425. So 0.425 would be 0.425. And then we're going to go up almost 10. So this is 0.4.5. This is 0.425. So we're going to go about 0.425 and up almost 10. move that over just a little bit. There we go. Okay, like that. And we've linearized the points. Now again, do not try and force this through 0, 0, because if you do, you're looking at a curve. You're not looking at a straight line. This is a straight line of data. We linearize this, okay? And it may look a little weird and say, well, it's not going through the origin. It doesn't have to. In fact, sometimes there's physical meaning behind something not going through the origin, because maybe the y-intercept actually means something. So I'm going to draw a line through all of that. Something like that. And, the best I can do to find this slope here, I can start essentially down at 0, and I can go up to, that's pretty close right there. So I'd be going up about 6 and over 0.3, roughly. So run of 6, rise of 0.3. No, not 0.3. Sorry. 0.2. Because we're only going from 0.1 to 0.3. Silly me. Okay. So now we have our slope, which is our K. K is our slope, which is your rise over run, which in this case, in my case, is about 0.6 over 0.2, and I get, let's see, what is that? That is 0.30, I think. So 0.2 is 30. 30 newtons per meter, right? And then we're going to calculate a percent error. To calculate the percent error on something like this, we're simply going to take the absolute value of the difference. So I had essentially 31 minus 30 divided by, pick one of the two, it honestly doesn't matter. 31 and times 100. So essentially 1 divided by 31 times 100, about 3.2% error. In other words, this right here is just showing how reliable it is to get the same result two different ways. Very reliable since you get very minimal error. And then lastly, it says explain the physical meaning, essentially, of the y-intercept. What does the y-intercept represent? If you look, guys, the y-intercept would translate way down here to the negative scale. What? Well, what's basically happened is the student has zeroed out the spring scale, or has calibrated the spring scale to not account for the weight of the spring. So the actual y-intercept, it represents the weight of the spring itself. Now, I will say that if you had graphed mass versus length, then you should say it represents the mass of the spring. So whether I'm saying weight because I graphed weight, but if you graphed mass, you should be saying mass. And if you graphed mass, by the way, you need to take your slope and multiply it times 9.8 times g. And you'll still get something around 30. So it represents the mass of the spring before masses are added to it. Well, again, Please feel free to pause and rewind as necessary. And thank you.